Welcome. Today we're going to learn about integration with trigonometric substitution, and this is example number 2. I have another video about this as well. So when do we use trigonometric substitution? If you look at example 1, the key thing is that we have a radical in the numerator. It doesn't have to be in the numerator, but we have a radical in the form that you see in item 3, square root of a squared minus u squared, where a squared is a constant and the u squared is some variable squared. And other possible forms that could also be useful when we're using trigonometric substitution are the forms you see in item 4 and 5. I do have a video that I already have on item 5, and today we're going to focus on the form in item 3. So the whole goal here obviously is to solve this integral. And we, as I said, have something in the form square root of a squared minus u squared. Well, if you look at that, you may recognize that that is related to the Pythagorean theorem. And so what we're going to do is use that radical and put it into a triangle, a right triangle, as you see in 3. And what we've done is we've put the u, square root of u squared, or the u, opposite of our angle, theta, and we have put the 2 in this particular case, which is our a, in the hypotenuse. And then in using the Pythagorean theorem, you would get the radical that you see which is adjacent to theta. So we have put all this together very nicely in a right triangle. And why are we doing that? Well, the whole purpose is that we are now going to use this triangle to create trigonometric functions that we are going to use to substitute for what we already have in our integral, and we're going to then integrate that. And it should be easier then to integrate. That's the whole idea. Okay, so when you have the form square root of a squared minus u squared, the best place to start is with the sine of theta. So if you look at our triangle, the sine of theta, in our case, using SOHCAHTOA rules, would be opposite of our angle, which in our case would be x, divided by the hypotenuse, which in our case is 2. So if you look at item 4, x over 2 is equal to the sine of theta. So that's the starting place, which I have noted in item 3. And then what we're going to do is we're going to solve for x. The reason we solve for x is because we're definitely going to need a dx. We're going to replace the dx eventually. So if you solve for x, it's much easier to calculate a dx. And it's also useful for other substitutions. So if you go to item 5, we simply take the derivative of both sides of item 4, and we get dx equals 2 cosine of theta d theta. Then in item 6, we utilize the fact that we want to also replace that radical. Square root of 4 minus x squared over 2 is equal to the cosine of theta. How do I know that? Well, go back to our triangle in item 1, and we use SOHCAHTOA rules. When you combine the square root of 4 minus x squared with the hypotenuse, you get the cosine of theta. Now, the reason that we chose that over 2 as opposed to over x is because the constant, you can always play around with a constant, but variables can get very messy. So it makes more sense to combine that radical with the constant. And so the cosine of theta works very nicely. And now at this point, we're all ready to go. We're going to make all our substitutions. We have everything we need. So if you go to item 2, you'll see the original integral. And what we're going to do is we're going to first replace the square root of 4 minus x squared over 2, which we already determined in item 6 as being the cosine of theta. So we're going to take that out and replace it with the cosine of theta. And you can see we've done that in item 8. Then we're going to replace the dx. Now that's the most common mistake students make. They replace everything, but they forget the dx. So if you go to item 5, the dx in our case is 2 cosine of theta d theta. So that's what we're going to replace the dx with. And again, if you look in item 8, you'll see that we've done that. Then we move to the denominator. Well, our denominator, we already accounted for the 2 in the denominator when we made that initial substitution, but we have not replaced the x to the 4th. So we have already determined what x is. If you go back to item 4, x is 2 times the sine of theta. So if you replace x with that and raise it to the 4th power, then you have what you see in the denominator in item 8. So at this point, we've made all our substitutions. Now the next step is to simplify things and then to integrate. So showed you in item 1, this is what we originally started with. After making all our trigonometric substitutions, you have what you see in item 2. Now I know that looks messy, but trust me, it's going to get better, okay? So let's move to item 3. First thing we do is we brought all the constants, we simplified the constants, which come out to be 1/8, and we bring that in front of the integral sign. We multiplied the 2 cosines in the numerator, so we have cosine squared. And then the denominator is sine to the 4th power. Now, that may not be an obvious integral on how to do that, so we're going to do a little bit of juggling here. If you look in item 4, what we did was we separated our denominator, okay? Instead of sine to the 4th, we made it sine squared times sine squared. And now, if you look at item 4, you'll see it's cosine squared over sine squared. Well, that's simply cotangent squared, and that's what we have in item 6. And then in item 5, 1 over sine squared, that is the cosecant squared, which we have in item 7. So the good news about making these adjustments is that we do not have a denominator anymore, so that's certainly a helpful thing. And now in item 8, we're going to do a little bit of juggling again. We're going to do some u substitution, where u in our case will be the cotangent. So instead of cotangent squared, we're going to have it as u squared. And the derivative of cotangent is minus the cosecant squared. So the cosecant squared becomes minus du. And now we have an integral that's very straightforward. The integral of u squared is simply u cubed over 3. And that's what we have in item 9. We brought the negative in front. Then we substitute back because the u was cotangent, so we've done that in item 10. So we're almost there. I repeated what we have in item 1, and this is where we are starting from at this point, but we're not done because the main variable here is theta, and we don't want it as theta, we want it as x because that's what we started out with. So we have to substitute back. So if you think about it, well, using SOHCAHTOA, the tangent of theta, if you go back to our triangle, and I've brought it back in item 2, the tangent of theta is opposite over adjacent. So that would be x over square root of 4 minus x squared. But we don't want tangent in this case, we're substituting for cotangent. So that would simply be the reciprocal of that, which would be square root of 4 minus x squared divided by x. So we're going to replace cotangent of theta with that, and you can see that's been done in item 3. We do a little bit more manipulation of our radical and our exponents, and we simplify, and you have the result in item 4. And that is integration with trigonometric substitution. Now go practice, practice, and practice some more.